All right, welcome. Thank you for taking that Chapter 6 test. I know it wasn't under ideal conditions. I'll get those graded and put into PowerSchool as soon as I can. But for today, we're going to go ahead and start Chapter 7. And there are several concepts in Chapter 7 that you likely have never seen before in your math academic careers. But I think you'll understand that by the time we're done here, you'll think that this was cool. It looks really impressive, some of the things you learn in this chapter, but I don't believe, in my personal opinion, that these things are necessarily difficult. Right? And most of the chapter is very closely related. These first couple sections are a little different, but it is all still going to fit together, trust me. But in this first section, we're going to talk about graphing what are called exponential functions. So maybe you've heard someone say something like, oh, this thing is growing exponentially. What does that mean? Well, if we look at this graph right here, this is an exponential function. You'll see towards the right, or towards the left, as we go to the right, it starts climbing very slowly. You might not even see that it's increasing here. But as we keep going along the curve, we see that it starts increasing at a greater and greater rate. And by the time it gets up here, it's increasing very rapidly. And if it were to keep going, it would get even steeper and steeper. That is the basic form of an exponential function. And so we see an example of that here in this picture in the notes. You'll see this curve doesn't exactly look like the example here, but this is real data. This is actually the human population on Earth over the last millennium or so, the last 1,000 years. So you'll see way back here, this was hundreds of years ago. As we go through time, the human population is not changing much. It's really not changing much. And at 1500 AD, so about a little over 500 years ago, there were 425 million people on Earth. Which seems like a lot, except once you keep going from that point, you see that the population explodes as we get closer and closer to the year 2000. At that point, there were approximately 6 billion people on Earth. But as you can see, it doesn't even stop there. And this graph is even a little bit outdated. We actually have a little bit more than this in terms of the population of Earth right now. But even just in the last 15 or 20 years, I'm not sure exactly how old this graph is, just in that short amount of time, the world population has increased by over 1 billion people. Throughout all of human history, up until 1500 AD, there were only 425 million people on Earth. We've more than doubled that total population just in the last 15 or 20 years. And you can think about what it would mean if this general exponential growth continued on, if the population kept increasing at an increasing rate. It's an interesting thing to think about, what might happen. But there are some experts that have suggested that just recently, in the past few years, that this curve has actually perhaps started to bend back. Still increasing, the world population is still going up, but maybe at a decreasing rate. And that might suggest that at some point in the near future, this curve will level out entirely and then maybe even bend back down. That's just speculation, though. Okay. But the point here is, something in the real world that follows this exponential growth function is the population on Earth. Now, unfortunately, in the last month or so, we've come up with another example of something that follows this exponential growth. You might know where I'm going with this. And it is the number of confirmed cases of COVID-19. And I'm going to limit this scope to just the United States. So you can see on this map of the US, the red dots represent confirmed cases. The bigger the dot, the more people in that area have the virus. And in the United States, this was recorded on April 1st, a little after 1 o'clock p.m. So by the time you're watching this, perhaps this has changed quite a bit. My guess is there are going to be a lot more than 190 or 200,000 people in the United States that are confirmed to have this. But at this moment in time, I actually want you to direct your focus to the bottom right here, to this graph. This is since January 21st. That was, I think, around when the first case in the United States, the first person to be confirmed to have COVID-19. And it took through the rest of January and the rest of February for it really to start taking off at all. On this graph, it actually looks flat, although that number is increasing. Excuse me. But just since about the middle of March, you see this graph really start to take off. And this is what the people who are in charge of building the models, the people who know what viruses like this can do, this is the reason why we're not in school right now. Because the more people that get this virus, the more likely it is to spread to more people. That's the reason for all this social distancing. But in any case, you can see that this is a logarithmic curve. It took forever for it to really start taking off, but when it did, the number of cases in this country is increasing at an increasing rate. And you can also see here on this site, the daily increase, again, all the way through January and February, not much there, but once you start getting into March, it really starts growing at an increasing rate. And in fact, the last date at this time that we have data for was by far the highest increase of any day. Okay. And I wouldn't necessarily expect this curve to continue increasing at an increasing rate forever. At some point, we're going to hit a maximum and go back down. But as of right now, this is this is an exponential growth curve. Okay. So let's go back to the notes here. Let's go back to our notes. And let's start looking at some of these functions. The reason this is called an exponential function is because the variable, x in this case, is in the exponent. That's not something you've seen before. So that's why it's called an exponential function. The x is in the exponent. So let's graph y equals 4 to the x power. Okay. And once we do that, we can state the domain and range and all of that. But before we graph this, I want you to think, what if I plug in some numbers for x, what's going to happen? So for example, let's say x is 0. If x is 0, then we have 4 to the 0 power. What would that be? Well, anything to the 0 power? That's 1. So if x is 0, 4 to the x power is 1. So we would know, for instance, that the point 0, 1 right here is going to be on this curve. Now what happens when you start putting numbers in for x that are bigger than 0? If x is 1, then you'd have 4 to the first power. That's 4. So the point 1, 4 would be on here. What if x is 2? What if x is 3? What if x is 4? You can keep figuring that out and seeing what that looks like. I'm going to take a shortcut here, and I don't want to look at this anymore. I want to use our favorite calculator, the Desmos Calculator. We should be able to type in y equals 4 to the x power and see what it looks like. So let's try it out. And there we go. That is the exponential growth curve that we would have expected to see. We said that if we plugged in 0 for x, we would get 1 for y. So the point 0, 1 is on the curve. If we plugged in 1, we would see if we plugged in 1 for x, we'd see y equals 4. The point 1, 4, also on the curve. Okay. So on our notes, we should graph that curve. Okay. If you need some points as guidance, you can always take this, go to edit list, and convert to table. That way you can get a few different points that are on here. And what you'll notice is, if you take that x value and take 4 to that power, that gives you y. 4 to the 0 power is 1. 4 to the first power is 4. 4 to the second power, that's 16. So on and so forth. Okay. So go ahead and either on your notes, if you can print them out, or if not, on a separate piece of paper, if you just write y equals 4 to the x power, and then just sketch a little graph of this. It doesn't have to be perfect. Just sketch the basic shape, what it might look like. We are going to figure out what the domain and range are for this function. Now, our notes can help us here. Backward explained the exponential function here. This is the parent function, f of x equals b to the x, where b is what we call a base, B-A-S-E. This is the base of the function raised to the x power. So in the example we're looking at, the base is 4. Okay. It says the domain is all real numbers. Now, you can just believe it because that's what it says, but for it to be all real numbers for the domain, that means it goes forever to the left and right. So if we go back to our graph, we see that this green line keeps going to the left forever and ever and ever and ever. Please don't make me keep scrolling, okay? It keeps going. It never stops, okay? And it also would need to go to the right forever. And if I zoom out here, you'll see it doesn't really appear to go really to the right at all. That's actually just kind of a trick of the eye. It is going to the right. Okay? It's just going up so fast that it goes up way, way faster than it goes right. This does actually keep going to the right forever. And to prove it to you, let's go back to our notes here. This is our function, y equals 4 to the x power. Can you put in a really, really big number for x? Will it let you do that? Could you figure out what 4 to the 1,000,000th power is? Is that a number? Yes, it is. Now, I don't think you can find a calculator anywhere that could tell you what number that is because it's so big, but we are allowed to have any number for x, and it will give us a y. So that is why the domain is all real numbers. So going back to our graph, we can put the domain is all real numbers. And you may recall that that's where we write that fancy looking R that has the extra stem. Like right here. Kind of like this. Okay. The domain is all real numbers because we can put in any number for x and get a value for y. There are no restrictions on the x values. Now the range, sorry, need to make that a note so I can type it and not be all italicized. The range, those are all the possible values for y that we could get from this function. Let me zoom back in here. Okay. So we're thinking about how high and how low this function goes. You might be tempted to type all real numbers in here as well. That would suggest that it goes up forever and it goes down forever. Does the function go up forever, up to infinity? Yes, we could zoom out here and it would keep going up and up and up and up and up. Okay, it does do that. Does it go down forever though? Well, a good way to check that is, it looks like it's going down as it goes to the left. So let's just put in a really small number for x, like -100. And it gives us this garbage, which this is a really, 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 really small positive number. 10 to the negative 61 power is a very, very small decimal. This would be, we would move this decimal place 61 places to the left. That would be 0.0000000000, 60 zeros, and then 6223015. So it's just an eensy-weensy little bit above 0. But it's still above this x-axis. I know it looks like it's on the x-axis, but if we zoom in really, really close, we see that no matter how far left we go, it's still above that axis. So like right here at negative 5.3, it's still above that axis. We can zoom in even farther and see it's still above that axis. So it's almost like these numbers get closer and closer to 0, but never quite get there. So for our range, we could say, we always started with a curly bracket like this. We'll say that the range is all y values such that y is greater than 0. Okay? It's all y values such that y is greater than 0. Okay? We've had functions similar to this where we needed to find the range before and we type something like this, or we write something like this. The y such that doesn't really add much. If you just wanted to put y greater than 0, that's fine. But this is technically the range for this particular function because we see that it gets closer and closer to 0, never quite gets there. And this is a greater than sign because it goes up in a positive direction as we go to the right. Okay, so that's the domain and range for example 1. So before we move on to any other examples, I do want to talk about this. Let's look at this function right here. This is certainly adding a little bit of complexity here, but what I want you to get out of this is the basic form of an exponential function, I'm going to go back up for a second, is f of x equals b to the x power, some base to a variable exponent. That basic function is still here, f of x equals b to the x, but we can do several different things to that function to make it look a little different. Okay. We can do horizontal translations. We can shift to the left or right. We can do vertical translations, shifting up and down. And we can change the orientation and shape of the graph. And I'm actually going to start by doing that. So what this is saying is if we change a, which is the number in front of the base, we can change the orientation and shape of the graph. So let's see what that might look like. We're just going to mess with the number in front of the base. So going back to our graph, get rid of the notes here. Okay, and let's get rid of this. We start with y equals 4 to the x power. So let's put a number in front of that 4. Let's put a number in here. What if we make it 3 times 4 to the x? What happened here? It looks like it starts about in the same place, but as we go to the right, it grows faster than the original one. It grows faster. You can actually take whatever y value is at a certain value of x, so this is 0, 1, take that y coordinate, multiply it by 3, and that's what it is on this function. So this is 0, 3. Where this function is at 2, 0.5, 2, the green one should be at 0.5, 6, because it's multiplied by 3. There you go. Okay, so it just multiplies every number by 3. Okay, so what if this number in the front was something smaller than 1? Like, what if it was y equals 0.25 times 4 to the x power? Okay, that's our purple one here. The blue is the original one. So we see instead of growing faster, it's actually taking a little bit longer to grow. It's still going up. It's still exponential growth. But since this number is so small in front, it's taking a little longer to grow. Okay. So, what if I told you there is a way to get this kind of exponential curve to go down as it went to the right? And what if I told you that had to do with the number that's in front? What kind of number would we have to put in the front here for it to go down as it goes to the right? Maybe you came up with the answer that that should be a negative number. Let's try it out. Let's put -2 here. Aha. There we go. That makes it go down. So if this number in front is negative, that makes it actually go down. This is no longer considered exponential growth. If it goes down like this would be called an exponential decay function. Exponential decay. Right? And by messing with that number in the front, we can make it grow at, or decay at different rates. So if we made this -0.5, okay, it takes a little bit longer to start decaying. Okay, so the smaller, or the closer to 0 this number is, the flatter it gets at the start. The further away from 0 it gets, the quicker it goes down. Okay, so just by messing with the number in front, we can make all these different adjustments to the shape of this exponential curve. Okay, but this isn't the only type of thing we can do. If we go back to the notes for a second, we see. So we've dealt with the orientation and shape. We've changed those. We can also translate or shift our curve horizontally or vertically. So let's do a vertical translation, or try shifting that curve up or down. This has to do with k, which is here. And this looks to be just tacked on to the end of the function. So if we add something to the end, we can imagine that would shift the curve up. And if we were to make this a minus some number, that would probably shift it down. So let's see if that's the case. We'll go back to our graph. Okay. Y equals 4 to the x power. I definitely don't want that to be blue. We'll make it orange. Okay, so let's add 5. Wonder what happened. There we go. So if we take any point on the blue curve, so like 0, 1, for example, to get to the orange curve, we just need to add 5. So that's why the orange curve crosses at 0, 6. And it looks like these are all 5 above. It looks like they get closer as we get up here. That's actually just because they're growing really fast. So for example, here, it crosses the blue line at 1, 4. If we go up 5 units, the orange curve should go through 1, 9. And it does. Okay. The blue curve goes through 2, 16. So the orange curve should go through 2, 21. And it does. So it looks like they're getting closer together, but it's still just shifted up by 5. Okay. How could we get this curve to shift down by, say, 3 units from the original? So how can we take the blue line and shift it down by 3? Well, we need our original y equals 4 to the x power. And then we just subtract 3 at the end. And that should shift everything down 3 units. And it does. Okay. So you can shift this basic curve up or down however many units you would like just by adding or subtracting at the end. Okay. So we are able to change the shape, and we can shift up or down. We know we can also shift this curve left or right. And that was by, if we go back to the notes one more time, if we want to do a horizontal translation or shift left or right, that's up here. We're actually messing with the exponent to do that. Okay? So if we want to shift something to the right, then we actually need to subtract something from the exponent. It works the same way as when we shifted other types of graphs, like parabolas or absolute value functions. It actually works the same way. And if this number is negative, so if we have x plus something, that will actually shift it to the left. Let's see what that looks like. Okay, so back to our graph. Let's say y equals 4 to the x, 4 to the x something. If we want to shift this graph to the, let's say, to the right, then we need to subtract something from x in the exponent. Okay, this will actually shift everything to the right by 3 units. And that's easy to see, like up here. Obviously, it's been shifted to the right. It doesn't look like it's being shifted to the right back here, but in fact, it actually is. These are not in the same spot. Okay, I would need to I would need to scroll in a lot more for you to see that. Just take my word for it. At every point on this graph, a point on the blue line, to get to the purple one, it's shifted to the right by 3. Okay, and that's easiest to see from 0, 1 to 3, 1. Shifted to the right by 3. If we want to go to the left, well, we just need to do the opposite and add something in the exponent. Oops. X plus 5. Okay, let's zoom out a little bit. And we see that it's been shifted to the left by 5. Okay, so by adding or subtracting inside the exponent, you shift it side to side. Adding or subtracting outside at the end shifts it up or down. And by multiplying by something in the front, that will change the shape. Okay. Now, we can mess with doing more than one of these things at a time. So we can go all out. Let's say I wanted my graph to grow less fast. I can multiply it by 0.4 or 0.5. I want to shift it to the right by 3. And I want it to shift down by 4. Okay. So we've taken our original blue graph, we've made it grow less fast by multiplying by a decimal here. So it takes a little bit longer to get going. We've shifted it to the right by 3, and we've shifted it down by 4. Okay, you can do all of those things at the same time. So even though this looks a lot more complicated than this, what I want you to get from today's lesson is that each of these different things has shifted or changed the curve in a particular way. You don't necessarily need to look at an equation like this and be able to tell what happened to it. That would be great. But it would be helpful to know that that is what's happening here. I don't just want you to type this in and then see what it looks like and be like, oh, that's what it looks like now. I want you to understand how each of these values is changing the graph. Okay, so we will go through the rest of the notes in tomorrow's video. If you want to go ahead and go through examples 2, 3, and 4, type those in, graph them, try out the domain and range, I would encourage you to do that. But that is what tomorrow's video will do. I will go through those 3 examples. You will see what they look like, what the domain and range are. And if you want to go ahead and get started on the problems for section 7.1, the homework assignment is on Canvas. You can go ahead and look at that. It's 3 problems like this. It will give you a function. You can type it in, see what it looks like, domain and range. And there is a word problem for the fourth problem, and I want to see if you can get through that as well. Okay, so just 4 problems on that assignment. You can start it now. It won't be due until next week, but you can go ahead and get started whenever you like. So if you have any questions about this video, please let me know. You can send me an email, and I will answer it as soon as I can. Other than that, that's it for today. Have a great day. See you.